We just published our full year report for 2024. The fund has been up 88.9%. And we spoke about some of the events of last year. I want to use this episode as a segue into what's going on right now, in particular, the whole chara about Deepseek and R1. And I want to wrap this in a context of reasoning models or inference models. And what I mean with that is that I think, for frequent listeners of this podcast, it's not going to be a surprise that AI has been at the forefront of our work, both investment-wise and, more importantly, also on a day-to-day basis, whether we attend academic seminars, conferences, meetings, companies, blog readings, book readings, all that kind of stuff. It's always been about AI, and I think the nascent development of reasoning models actually puts the AI question at the forefront, and it puts it in a very interesting context, puts it even in a more interesting philosophical context of, okay, what does it actually mean to be intelligent? We've had, if we go back in history of AI, the ImageNet moment was a moment where we realized that we can teach machines how to classify things based on vision. And computer vision had a run for over 10 years, still has one, but mainly the idea that you can actually see things and then classify things. Fei-Fei Li spoke about this in the context of The Blink of an Eye, a book that explains the Cambrian Revolution through the lens of living beings developing eyes or sight. And that brings up the question of what is actually sight. And I'm going to talk about this a little bit more. We then had the next ImageNet moment, which was ChatGPT in 2022. And that was the context of knowledge. So the ability to understand knowledge in a more general way and extract knowledge. And that was the birth of Gen AI. And that just meant that we went from classifying things. So if you take Google search, which is a classification engine, towards Perplexity, which is a generation engine. So we are able to not just know what's up, but also generate insights of what's going on. That's Gen AI. And reasoning is the next step. And I think, to be fair to OpenAI, they've come up with O1 a while ago. Deepseek now has R1, and we're going to have more of these types of developments. What is reasoning? And we spoke about this in our full year report. It's on the website. We spoke about actually some of the ideas that we caught from Neurips 2024. We didn't attend the conference, but just reading through some of the papers, I figured that is one of the more interesting developments. And what does reasoning really mean? Reasoning means that you have the same idea like in large language models, which is you try to store knowledge in latent space, so which means in some sort of machine understandable space. Now the knowledge is a little bit different in reasoning versus in large language models, in a sense that in reasoning, what the knowledge is how to solve problems. And the canonical example is that if your task is, let's say, you want to optimize an earnings stream for a company. Let's say you're asking R1, this is my company, this is my sales, this is my profit, this is blah, blah, blah. How much should I invest? So things along those lines. The model quickly understands that this is a quadratic programming problem and then goes to the template that has quadratic programming already stored in a sort of sequence way. So it knows how to solve these types of problems and then applies the variables accordingly and solves the problem. So another example would be, give me the best restaurant in Palo Alto, California. this is a classification and a sorting problem. So it goes very quickly, understands the classification side of things and then the sorting side of things, and attacks the, so that's where the efficiency comes from. That's where inference becomes really interesting. And then, of course, the question that the market is asking right now is, okay, well, it looks like we can do this at a much cheaper rate. Now, we're going to discuss this also, but that's, in my opinion, a much more that's a much more harder question to answer, simply because we had O1 and these types of models that came out of Silicon Valley, which clearly require a lot more training than Deepseek claims that they have been training on, and therefore it's a little bit more difficult to classify Deepseek. It could be that they're right. It could be also that they're wrong, that they had access to a lot of GPUs and that they don't disclose that because of sanctions, or that even more, if you want to go down the conspiracy route, maybe they've been financed by the People's Liberation Army or something like that. So who knows? And I don't want to speculate about this. I just want to say here that I am not so sure that we should now conclude that all the AI infrastructure investment that we're making is useless. I actually think the exact opposite, which is our conclusion as a fund. And the way we see the future of AI is the interesting part of AI is actually real-world AI, and we're going to discuss that also. This is the Not Even Wrong podcast. It's January 28, 2025. This is Krim Telco. For the year, we're down 5.2%. The market's up 3%. We're underperforming by 8%. We've had a drawdown in Nvidia and also a slight decline in Tesla over the last couple of days. Tesla is coming up with earnings tomorrow, and I think people are generally bearish on the margins and the outlook and things along those lines. I just want to leave it open. We are obviously incredibly bullish on Tesla. It's our largest position, and the reason we're interested in Tesla is because of Cybercab, Optimus, energy, and the general application of AI towards transportation and energy. So those are the kinds of big themes that we believe will stay with Tesla. And by the way, we'll stay with Tesla with or without R1. So that the relationship there, in our opinion, is not so important. What's more important, of course, is competition. Competition is always important, and that's been the case since Tesla is operating in China. Chinese competition is serious. We have utmost respect for the car manufacturers and the AI applications of those car manufacturers. The thing that we think makes Tesla unique as an investment in real-world AI is the fact that they have figured out how to store an enormous amount of data to create the ground truth for driving, and therefore are able to teach FSD how to drive. So it's not about the models, and it's not about the algorithms. It's actually about the data. And if you look at some of the naysayers like Mark Benioff or Sebastian Thrun and people like that, who were really happy to proclaim the end of Silicon Valley's domination of AI and then some sort of nascent Eastern domination of AI because of Deepseek, I think that might be true, that might be happening. But as far as Tesla is concerned, first, Tesla is a large Chinese company, so we're not necessarily betting against China here. But more importantly, it's really about the data. And the data, again, what Karpati and his team have done almost 10 years ago when they created things like shadow mode and all these driving observational technologies that Tesla is now using to train their models and to keep training their models. That is really the advantage that Tesla has. Now, of course, that can also be replicated. Let's say Com.ai is trying to do similar things, but the scale and the industrial depth of Tesla, in our opinion, is going to be very difficult to compete with. And to paraphrase Brian Chesky from Airbnb, the rate of growth of a company is defined by the rate of growth of its founder. And well, we all know what that means for Tesla. So in that sense, we're very comfortable with Tesla. As far as Nvidia is concerned, here's the thing with Nvidia, right? If you want to, the way this company has evolved over the last 15 years since we're basically invested in the company, and we've been fortunate enough to ride this company from whatever 20 billion up to 3 trillion, not fully invested, and we've made a lot of money, but not the kind of money that you might think. It's not we had a 100% position, so let's just be clear about that. But nevertheless, we've been following Jensen for a long time, and the thing with Jensen is that the one thing that I like about him is he is incredibly good at articulating the next 10-20 years of his company, and he's been very good at that since the 1990s when he founded Nvidia. So could this change now? Of course, this can always change, but the way we see the future of Nvidia is it's in real-world AI. And also to bring in another context which is important in today's conversation about Deepseek, and that is Ilya Sutskever's talk at Neurips. And I think that's what the market is pricing now. Basically, what Ilya said is we're done with training because we've trained on all the data, so now other things will matter, and i.e. Reasoning. And of course, we don't disagree with that, but what Ilya is referring to is the training of internet-based data and not real-world data. And what real-world data means is you want to build inference engines for physics, inference engines for robots, inference engines for chemistry, inference engines for biology. You want to have in virtue development of drugs, of heat shields for Starship, of energy products for batteries. What we mean with that is that you want to actually convert the whole supply chain of the world, the industrial supply chain of the world, from try and error in physical space to try and error in virtual space, and then only tape out when you already have a product that is hopefully going to have all the things that you need, product market fit and so on and so forth. You have inverse engineering, which is you start with the properties that you want and then have the AI engineer the product. In other words, the engineer is creating the machine that solves the problem and doesn't solve the problem anymore. That is has been our slogan for a while, and that's where we see Nvidia. And therefore, we disagree with Ilya that we're done training. In fact, we're just starting training because the four-dimensional world, 3D plus time, has been incredibly underdeveloped. I mean, we've done barely anything. In fact, the only thing that we've done at scale is FSD and some of the humanoid robot companies that are investing in that space. We've seen some attempts, let's say, by companies like Ansys, which just got acquired by Synopsys, to build physics inference engines. We have Omniverse and the simulation engines that Nvidia is offering, but those are all still nascent, and we believe that there is going to be a lot more opportunity on that front. So to summarize our positioning right now, large position in Tesla, large position in Nvidia for real-world AI reasons, and real-world AI is going to be solved in many ways, but in particular on transportation and energy. Energy is sort of a wrap for any kind of economy, any kind of company, any kind of investment. In the end, it's going to be driven by energy one way or the other. So if you invest in energy as a whole, if energy is actually your investment, and you hit the right data points as far as what the company can do and how the company can grow, and just to remind our listeners, the PQ idea of Peter Thiel. In other words, P is the amount of value you create for society, and Q is the amount of value you capture for yourself. And if that P is 10x Q, but overall you still PQ is large, you will generate wealth. So that's where we see our portfolio. Now let's talk a little bit about these inference models and what that means for AI. And I want to really digress, inspired by a recent podcast, the Weights and Biases podcast with one of the Sequoia partners, David Kahn, which I thought was interesting. David is, in my opinion, is an interesting person, actually. He's one of those people that if I just saw his background, I would say, nah, what is, not too interesting, very little experience, partner at Sequoia. Sequoia is not exactly we're not the biggest fans of Silicon Valley venture capital. Let's just leave it at that. But nevertheless, he's one of those examples that you sort of the exception that confirms the rule. In other words, he is actually an interesting person, and he brings up Hofstadter's Gödel, Escher, Bach, right? And the question of what is intelligence, and the question of what is religion, and what is consciousness, and what does all this mean, and I think in that context, let's start with what does an inference model really do, and then try to digress into maybe Hofstadter's Gödel, Escher, Bach, and try to wrap it up in terms of the way we see it, what we think intelligence will mean in the next, let's say, 20 years for humanity. So first, what are inference models actually doing? So let's, like I said in the prelude, a little bit of history. ImageNet learned how to classify things. What is a cat? What is a dog? What is a flower? Large language models learn how to connect flowers with weddings or funerals and things like that. So what large language models are able to do is they say, well, there's a relationship between this and that. And if you ask for a funeral, then maybe flowers will be in the context of a sad event, versus if you ask for a wedding, flowers will be in the context of a happy event. So they're able to extract that type of knowledge, and that's because of Ilya and other people's work. I'm just using Ilya Sutskever here as a sort of placeholder for many other people, so I want to be conscious of that. But he is the face of the large language model space because he was the chief scientist at OpenAI, which really sort of brought this whole thing to bear. Now, what large language models do in a very sort of big picture way is they store knowledge in latent space such that machines can query that knowledge and also find relationships that are useful for humans. And to use David Kahn's expression, they also map onto the user. So after a while, they're able to understand what the user actually wants and thinks and how she wants the information to be presented to her. So in other words, if you're a chemist, you're going to ask about water in a different way than if you're an athlete, right? Water for an athlete is fuel. For a chemist, it's an ingredient. So things like that. And now inference model, what are inference models doing? And that's where I think Neurips was really interesting. We started working on this, I would say when O1 came out, OpenAI O1, somewhere in the fall of 24. And then at Neurips, we just saw a couple of papers, and one of them we just recently discussed. It's on our website. Just look at, I think it was Neurips part 14, Neurips 24 part 14. So what is an inference model actually doing? Well, an inference model is trying to learn tasks, right? It's trying to learn, okay, there are different classes of tasks that we can map to queries. And like I said, for example, the task is give me the best restaurant, the best taco restaurant in Palo Alto. What is that? What kind of task is that? Well, it's a classification task and a sorting task. Classification is taco restaurant versus pizzeria, and that's the classification, and the sorting is I want the best versus the worst. Or you even have to classify what is good and bad and so on and so forth. So these are the kinds of problems that this query requires to be solved. And instead of having a sort of one-shot attempt to solve this problem and go through all the possible iterations that we could have. So in other words, we could, now the model has to first, identify what is a restaurant, and then somehow throughout its inference time, we realize that what you're really asking for is classification and so on and so forth. And then maybe you have trained it through reinforcement learning to be a little bit faster in coming to the solution. Why not just map it to a template that says, oh, this is a classification problem. So where's the template for classification is here. Let me apply this. So you're kind of, if you another analogy would be if you think of a binary tree of possible paths that the inference engine could go when solving the problem, you just map it right to the part of the tree where it's relevant, and then let it solve the problem going forward for there. So what does that do is it makes it more efficient, faster, runs on a lot less hardware, things like that. And that's really what, in our opinion, inference models are doing. And if you now lean back a little bit, take a big picture view, like always in AI, it starts becoming philosophical because it sort of puts one big question in front of your eyes, which is, all right, what exactly are we doing then, we humans, right? We thought that when large language models came out, we were just parrots, right? We were reproducing something that we've already learned because that's what large language models are doing. And now with these inference models, we're just templatizing solutions. So if I'm an analyst at a hedge fund, I'm talking to a founder that is investing in databases. I'm just going to map, okay, well, a database, yeah, okay, I've done this, and this with database, so she's going to try to do this, and that. What's new? So we're just mapping solutions to some memory of prior attempts to solve similar problems. And you could say, well, yeah, maybe that's really what we're doing. And I think there's nothing wrong with that. And we believe that that's where the models will be going. So you will have faster inference at lower cost. That's in my opinion, the conclusion here. By the way, we've seen this also in the past. Let's say the MLSys conferences that we attended were always those types of conferences where you have maybe 10% of the attendance that you would have at a Neurips conference, but maybe 3 times more importance, because what MLSys is really doing, ML Systems, MLSys stands for ML Systems, those are the kinds of people who really think hard about the nitty-gritty of the hardware and the software that is applied, the actual math that is done, and how that can be made more efficiently. So when you looked at those conferences and what people were talking about there, a lot of times people were talking about things like quantization, of neuromorphic computing, of the question of how much precision do you need. So those are all kinds of things that you have, let's say the Deepseek R1 paper discusses, right? How can we cut this short? How can we reduce the amount of compute and not give up too much accuracy? And if you now add this templatization of problem solving, then you're not just reducing the amount of compute because you're less precise or you're sort of cutting corners, but you're actually even cutting the tree of possible, if you want to think of it like in sort of Monte Carlo tree search type context, you're cutting the search into a very short part of the tree that is relevant for your problem. So the task of an inference engine is to identify the problem. So what does that mean actually in the real world? That means that, of course, you're going to have to be very good at prompt engineering, and you have to be able to create the kind of prompt that triggers the chain of thought that is actually relevant for your problem. And it's another way to actually formulate inference engines. They are automated chain of thought engines. So they're very good at understanding, okay, this problem requires this type of COT, chain of thought being the idea that you can extract more knowledge from a model by having a sequence of prompts that drives you through a fixed amount of weights. So you're not changing the weights of the model, but you're sort of navigating through the model more efficiently with this chain of thought, and therefore extract more out of the model with a different type of prompt engineering. And that was probably the biggest breakthrough in Neurips 2023. So this is a sort of sequence of that. In 24, we realized that we can use this for inference engines, and O1 and R1 are the manifestation of that. So where does this all leave us? I want to end this episode with a little bit of philosophy, again, leaning on David Kahn's comments at the Weights and Biases podcast, links in the show notes. He spoke about the Gödel, Escher, Bach. And what does Gödel, Escher, Bach actually mean? What does the book mean, and why is this relevant for AI? Well, what Hofstadter did back then in the 80s, I believe, when it came out, he looked at Gödel and Escher and Bach, 3 diverse individuals Kurt Gödel and David Escher and Johann Sebastian Bach. And what they all did is they created these self-reference models in math, in music, and in painting. And what Hofstadter tried to do was map this to the human brain and say, well, that's kind of how the human brain works. And I actually always felt that the real strength of Gödel Bach is described in another book called I Am a Strange Loop, which is the explanation of what Gödel Bach actually means. And in I Am a Strange Loop, I think Hofstadter is a lot more articulate about what he means, or he explains Gödel Bach. And the I'm a Strange Loop actually talks about exactly that, the loop. And if you think about this, it's more like an avalanche, you know, for let's say free skiers out there. You know what I'm talking about. How does an avalanche start? Well, it starts with a small snowball, or the snowball effect, right? You start somewhere and then the whole thing grows into a snowball, and lo and behold, we have an avalanche. That's kind of how we humans operate. The brain is a bunch of neurons that somehow catch on to something and evolve, and that's what we call a personality or consciousness. It's how these things evolve, and that's why no human being is alike. In fact, no human being is even alike compared to herself just a while ago. Because these loops keep looping, inputs are coming, and things either stick or they don't stick. So that's kind of the way I understand it. And now if you map this now to the AI side of things, you could say the same thing. Well, what is AI? It's a bunch of inputs, it's a bunch of neurons, and they get triggered. And the way they get triggered is obviously based on some sort of algorithm that the developers of the algorithm specify. And the less priors we use, and the more general we keep it, the more intelligent this thing will become over time, because it will trigger itself towards the kind of solutions that are necessary for the AI to evolve and develop its task. If you use another analogy, which is biological evolution, what that means is that we all start out with the same, let's assume we're in the Cambrian age, and we have multiple species that all start out with the same open general framework, and then they start moving around and developing and so on and so forth. And each species loops around different types of events, because it gets exposed to different types of events. One species has a little bit more sunlight, the other species has a little bit less sunlight, and so on forth. And they start looping and developing niches, and you add genetic mutation to that. So you're not just, what that means is that you actually even change the algorithm a little bit through genetic mutation, which would be the Darwin argument. And lo and behold, we have a Cambrian revolution. We have different species evolving into different niches, and that's what we call intelligence. We have, a certain intelligence. Let's say a dog can smell really well, humans can see well and think, and fish can swim fast, and so on and so forth. So they have all different strengths, different types of intelligence, and we're basically focusing on the kinds of intelligence that help us succeed in the particular niche that we're operating in. So to summarize this part of this episode, I think we're now at a point in AI where we're saying, all right, we have a way to store knowledge, and now we have found ways to store problem solutions. And what it's all about in the end is finding solutions to problems. So if that's what it's all about, if we are basically focused on finding solutions to problems, then we are at a point right now in the evolution of AI where we can not just store all the knowledge that we trained on the internet, but also find useful solutions for problems. And if we extrapolate this to the next stage, which is the stage that we're investing in, which is real-world AI, you can say the same thing here. First, what we need is knowledge, so we need to understand how the real world actually looks like in terms of how things relate to each other, particles, matter, physics, chemistry, all these things. I mean, we're just very nascent here. We have, if you want to use an analogy, we're in the stone age of real-world AI. This is just the beginning. We have robots like FSD that are somewhat able to navigate the real world because they understand the relationship between physical objects and dynamic objects. But we're just in the beginning. Think about, for example, physics, particle physics, the work that is done at SLAC or CERN. All this type of information can be stored the same way that the knowledge on the internet has been stored in LLMs and then queried for generative AI. In other words, we could do things like inverse design to understand condensed matter physics better, and therefore, maybe come up with batteries that are better, and so on and so forth. So that's where we think this whole thing is going. Whether our timeline is right, or maybe we're too early about this, that is the risk we're taking. But that's the excitement, and we believe that, therefore, we're just at the beginning of actually storing all the real-world knowledge, and we're not even close to having inference engines that then solve the problems that we could solve with that kind of knowledge. Thank you.